Okay, so we've taken a look now at the concept of confidence intervals for confidence intervals around the mean of a distribution and confidence intervals around a proportion. Next, we're going to take a look at, we're going to get started looking at hypothesis testing, basically by just describing what it is and what these things called the null and alternative hypotheses are, and how to properly specify the null and alternative hypotheses. All right, so we're going to understand the basis for hypothesis testing, discuss how to identify the so-called null hypothesis and the alternative hypothesis, and also talk about whether, when you're doing a hypothesis test, you want to use what's called a one-tailed test or a two-tailed test. So, we have been drawing inferences about population means based on confidence intervals. So, in the case of how much money have Pennsylvania's been spending or Pittsburghers been spending on internet purchases, we were able to say things like, based on our sample, there's a 95% chance that the true mean of the amount of money that Pittsburghers spend on the internet is between, some low end and some high end of some interval. And of course, we can narrow that interval by increasing our sample size. We can also to a less satisfying way, we can narrow our confidence interval. We can narrow our bounds around the mean by reducing our level of confidence, that's generally not a good trade-off. Okay, but what if we wanted to test something specific about the value of this mean? That is, we want to test whether the mean is equal to some value or greater than some value or less than some value. We want to do these kinds of tests. All right, here are a couple of illustrations of the two different kinds of hypothesis tests we could do. Is the mean income of Pittsburgh registered nurses over $40,000? Okay, well, to test that, we're going to create what's called the null hypothesis. You can think of this as the default hypothesis, or I'm almost reluctant to say this, but this is the hypothesis that you want not to be true. Okay, so the null hypothesis is the thing that you fear might be true, that you're trying to disprove. And then the alternative hypothesis, in this case, would be that the mean income of Pittsburgh registered nurses is, in fact, greater than $40,000. Okay? So the alternative hypothesis is the hypothesis that we're testing, and the null hypothesis is the one that we either assume or fear is true without having done any further analysis. All right, so this is a hypothesis where the alternative is testing whether the mean is greater than something. Here's another form of hypothesis here. Does our new integrated development environment affect programmer productivity? Here, the null hypothesis is that the new integrated development environment, the new IDE, does not affect programmer productivity. That is, developers using the new IDE have the same productivity that they have before. Our alternative hypothesis is that there is an effect. In this case, we're testing whether the impact of the IDE, whether the mean productivity is not the same as the productivity prior to introducing the integrated development environment. Now, this hypothesis, these two hypotheses, are testing for an effect. They're not testing for an improvement, okay? If we were testing for an improvement, then our hypothesis test would look like the one that we did for registered nurses. Here we're testing for an effect. The effect might be beneficial, or the effect might be, counterproductive. Okay, so what we're trying to do here is to test whatever our alternative hypothesis is against the null or default or expected or feared null hypothesis, okay? Let us assume we want to measure a productivity in terms of lines of production quality code written, which is a really bad way of testing programmer productivity. But it is, unfortunately, a means that some managers are prone to using. Okay, so historically, we have, in our development group, we have identified how much code developers write in a day, and we have determined that they have, on average, developed 1,000 lines of code per day. Now, I would like to hire these programmers. These programmers are profoundly productive. I don't know anybody who can write 1,000 lines of code per day. But just for the sake of argument, we're assuming that our average productivity in the past has been 1,000 lines of code per day. And so our null hypothesis is that the new integrated development environment is not helping us. Therefore, the mean after we've introduced this new integrated development environment is still 1,000. The alternative hypothesis is indicating that there is some kind of effect. That is, that either programmer productivity definitely goes up or definitely goes down. Why do we do things this way? Philosophically, one of the great dangers in science and in just discussion of facts about things is that humans have including statisticians, including scientists, have a behavior of believing that something is true and then seeking evidence to support that thing is true. And so we're going to specify as our null hypothesis, our baseline hypothesis, is that things have not changed. Things have not gotten better. Things have not gotten worse. Things have not changed. All right, so this tries to guard us against seeking data that supports something that we believe or something that we want to prove, okay? So we reject the null hypothesis in the case where we can prove with a very high degree of confidence that the null hypothesis is false. Okay, so we reject the null hypothesis if we have very definite evidence that the null hypothesis is false. If we don't have very significant evidence that the null hypothesis is false, then we say that we cannot reject the null hypothesis, which is equivalent to saying that we are unable to accept the alternative hypothesis. Okay, if we cannot strongly reject the null hypothesis, then we are unable to accept the alternative hypothesis. All right, so if we do have strong evidence that our integrated development environment does affect productivity, then we say we can reject the null hypothesis. We conclude that the mean after introduction of our new integrated development environment is not 1,000 lines of code per day. Therefore, we accept that the alternative hypothesis is correct. Now, I just made a I just made a cultural boo-boo there, depending on how strict in terms of language the statistician that you're talking to is. So there is this problem, as I said, of people believing that something is true and then going out in search of evidence to support that what they believe is true. Really strict adherence to this idea that the null hypothesis implies that the status quo continues, that nothing has changed, that there's no improvement, that there's no disimprovement, everything is as it was before. Really strict adherence of that would not say that we are willing to accept the alternative hypothesis. They are only willing to say that either we do not reject the null hypothesis or we do reject the null hypothesis. The practical impact of rejecting the null hypothesis is that you do accept the alternative hypothesis. I mean, that's the practical effect. You know, if you reject the null hypothesis, that implies that you are going to accept the alternative hypothesis, and yet, to many people, it's forbidden to say that you accept the alternative hypothesis, and you're required to say instead that you reject the null hypothesis. Okay, now we have to strongly contradict the null hypothesis in order to be willing to accept the alternative hypothesis. Here's another place where casual analysis tends to break down among people who are not trained as statisticians, who do not have scientific math kinds of backgrounds. It's often the case that people will accept flimsy evidence that the null hypothesis is incorrect in order to reject that and accept the alternative hypothesis instead. Well, we now have enough background that we can be specific. We can specify numerically what we mean by strongly contradicting. All right, and this is going to involve our confidence intervals and our levels of our levels of confidence. So here is this famous tea tasting experiment. I have a clear memory in my mind that we have talked about this before, but I can't find in my notes where we've talked about it before. So I will assume that I am misremembering, and we'll start from the top here. Okay. So a lady says that she can taste a cup of tea to decide whether milk was added before the tea was added to the cup, or whether the tea was added first and the milk was added afterwards. Okay, and we're going to use aisle to identify this. Now, if she does not have any ability to really tell the difference between tea first versus milk first, then the probability that she's going to guess correctly is going to be 0.5. There's only two possible outcomes. And we're going to set things up in such a way that half of our tests have the milk added first and the other half of our tests have the tea added first. All right, so to set up our experiment, our null hypothesis is going to be that she can't tell the difference. All right, our null hypothesis is going to be that she cannot tell the difference. And our alternative hypothesis is therefore going to be that she can. All right, continuing on. Okay, so null hypothesis is that she can't. Alternative hypothesis is that she can. We're going to prepare 8 cups of tea, 4 of which have the tea added first and the other 4 of which have milk added first. And we are going to present these cups to her in some random order. In fact, if we're really being very careful about this, we've got one person who is creating the samples of tea, and we've got some completely different person who didn't see the creation of these cups of tea, taking these cups of tea and delivering them to the lady, the test subject. Okay? Now, we are going to reject the null hypothesis if the data supports the alternative hypothesis. Supports the alternative hypothesis, but we have to have very convincing evidence in order to reject the null hypothesis. All right? Now, suppose that she is guessing. And nevertheless, even though she is guessing, she gets all 8 of the cups identified correctly. Well, the probability of getting all 8 of these correctly, given that for each one there's a 0.5 probability of her guessing correctly, is 0.5 to the 8th power. Okay, which is 1 over 256. Which is, a very tiny probability. Here we're saying approximately 0. Okay, so there's almost no chance that she's going to be able to get all 8 correctly if she really is guessing. I want to emphasize that this is not a fair race between the two hypotheses. That is, in this particular example of tasting tea, it's not going to be like majority rules. We're not going to believe if she gets 5 right out of 8 that she really can tell the difference. That could just be luck. And in fact, let's look at our binomial distribution to see that that's the case. Let me pull up my binomial distribution widget. All right, so we're going to do 8 trials for this experiment. And we're going to compute the probability that the number of we're going to compute the probability that the number of correct identifications is greater than, let's say, 4. Okay, greater than 5. No, greater than 4. We want greater than or equal to 5. Okay, so the probability of success, if she's guessing, is 0.5. The probability of her guessing correctly more than 4 times, that is 5, 6, 7, or 8 times, is 0.3633. So the probability of her guessing correctly 5 or more times is less than 0.5, but it's still not a very small probability. This is where our idea of the alpha comes in, and we would be interested in having an alpha of, in this case, less than 5%. And let's notice that if we crank this up to greater than 6, all right, if we say that if we do 8 trials where there's a 50-50 chance of the milk having been added first or the tea having been added first, and the lady gets more than 6 identifications correct, then if she's guessing, the probability of her getting more than 6 correct is less than 5%. And so if we choose 5% as our threshold, as our alpha, we would say, okay, at a 5% alpha level here, we're willing to reject the null hypothesis that she can't tell, which inevitably means that we're going to accept the alternative hypothesis that she can tell. And in fact, so supposedly she got all 8 correct. She got more than 7 correct. And the probability of her being able to do that, if she's just guessing, is about 0.4%. Okay, so this still isn't, perfect. We still don't know for certain that she can identify cups of tea. It could be that in this particular test that we gave, she was just phenomenally lucky and happened to guess correctly 8 times in a row. But the probability of that, as I said, is 0.4%. Okay, so in order for the null hypothesis to be rejected, there has to be very strong support for the alternative hypothesis. Okay, I think this repeats basically things I've already said. So a statistical hypothesis is some assumption about some population parameter. And we have the null hypothesis, which usually assumes that the parameter hasn't changed or is equal to something or is less than or equal to something. And the alternative hypothesis is generally the opposite of this, which we are hoping to demonstrate is true. So the alternative hypothesis is the thing you want to demonstrate it. And the reason we call this the alternative hypothesis rather than the null hypothesis is to, give ourselves a little reminder, hey, we're not looking for data that supports our theory. We're only going to be willing to accept our theory if the odds are very great that the opposite of our theory is false. All right, so here's just a couple of examples of alternative hypotheses. A community's average yearly spending on computer supplies is greater than $40 per household, let's say. Providing restaurant customers with calorie information reduces their consumption of calories. Okay, these are things that we might wish to demonstrate, that we might wish to prove. And so the null hypothesis is going to be the opposite thing. Now, the opposite of greater is going to be less than or equal, and the opposite of reduces is likewise going to be greater than or equal. Okay. Now, I want to, it's as a syntactical or a semantical little hint here about how to set up your null hypothesis. The null hypothesis always contains equality. Now, the null hypothesis might indicate that the mean of some, some parameter, in this case, the mean of some distribution, is exactly equal to some specific value. Or it might indicate that the mean is less than or equal to some specific value, or greater than or equal to some specific value. But there's always an equality in the null hypothesis, which means that the alternative hypothesis has to not include an equality. So the alternative hypothesis has to be that some parameter is greater than some value, or not equal to some value, or less than some value. Now, depending on whose book you're reading, the alternative hypothesis might be labeled as H sub 1, or might be labeled as H sub A, okay, A for alternative. But the null hypothesis is, in essentially all writing, indicated as H sub 0. Here's some examples to try out. We're just asking you to state the null hypothesis and alternative hypotheses. We're not asking you to actually compute anything here. You are a purchasing agent for Boeing 737 MAX parts. In order to be safe, some part has to have a mean life exceeding 500 hours of flight time. All right? So we get a sample of 400 devices, and we assume that this is a correctly, carefully collected set of 400 random devices. That is, these are not 400 devices carefully selected by the vendor to try to prove that their parts are good. We have obtained these parts without any involvement from the vendor. And in this sample of 400, we compute that there's an average of 510 hours with a standard deviation of 70 hours. What is our null hypothesis here? Where our null hypothesis here is going to be the thing that we fear might be true, which is that these are not going to meet our expectations. In other words, our null hypothesis here, I'm going to pull up Notepad to draw on here. And let me shrink my font down to something that's not so outrageously large. Okay. So, for our first test, for our first example here, our H naught is going to be that the average life is less than or equal to 500 hours. Notice the equal sign in the null hypothesis. And what we're hoping is true, but may not be true, I'm going to use HA here. Our alternative hypothesis is that the average, life, the average life is greater than 500 hours. All right, so the average life has to exceed 500 hours. All right, we're not asking for a solution about this, because notice that nowhere in this description have we specified a confidence level. So we're not asking to compute whether the alternative hypothesis should be accepted or whether the null hypothesis is accepted. We're just asking to state what they are. And then for the second one, a cereal manufacturer wants to test the performance of its machines. The machine is designed to issue 12 ounces per box. Quality control wants to test for departures from that. We collect 100 boxes at random, and we discover that for this sample, the average is 12.1 ounces, and the standard deviation is 0.5 ounces. All right, so does that mean that our machines are departing from 12 ounces? All right, so departing, of course, means different from, which means not not equal to. So our null hypothesis is that the weight is equal to 12 ounces, and our alternative hypothesis is that the weight is not equal to 12 ounces. Okay, now this is, I had previously said that that the null hypothesis is going to be often the thing that we fear is true, or that we're trying to disprove. This particular example is a little bit upside down from that, because of course in this case we want not to be able to reject this null hypothesis. We want to be able to conclude that the machines are satisfying the null hypothesis, but the math is the same. All right, and then this final one, vocational training claims graduates spend less time unemployed. Suppose high school graduates are unemployed for 25 days a year. We sample 100 of our graduates and discover that they are on average unemployed for 19 days a year. Does this show that graduates from the vocational program spend less time unemployed? Well, here, our null hypothesis is that the unemp rate is 25 days. And our alternative hypothesis is that the unemp rate is less than 25 days. Now, sometimes your statements of the null hypothesis and alternative hypothesis will be framed in this way: that the null hypothesis is that the unemployment rate is equal to some number, and the alternative is that it's less than that number or possibly greater than that number. That's perfectly acceptable. I could just as well say that the unemployment rate is greater than or equal to 25 days. That's our null hypothesis for our graduates. And as an alternative, that the unemployment rate is less than 25 days. All right, now casually here, without actually doing computations and choosing a confidence interval, 19 days does appear to be a fair amount less than 25 days, so we might, before we actually do the math, think that, yeah, we're probably going to be able to reject the null hypothesis in this case. But it's always very risky to apply intuition rather than actually cranking out the numbers.